Okay, there you go. So, okay, so here's the agenda. So we're going to start with some important sums and sequences, and then we're going to go into the actual functions we're going to be doing asymptotics on. So first iterative functions, and then recursive functions, and then we'll talk about like best case, worst case. So like when to use O, when to use omega, when to use theta. And then at the end, if we have some extra time, then if you have a question you wanted to, like a function you wanted to do asymptotic analysis on, we can do that. So, okay, so I think that's good. So we'll just start into number one, so the important sums and sequences. So I guess, yeah, number one. So there's two main sums that you need to know to do these problems, and they always pop up whenever you're, or if you're doing it the right way, you'll see these sums pop up. They might be a little bit hidden, and you might need to do a little bit of like small algebra, like factoring out a number, but you'll see these in the functions that we'll do. So the first one is an arithmetic sum, which hopefully everyone has seen before. So the easiest example is like 1 plus 2 all the way to like some number. Actually, I'll use m instead. So it doesn't like the important thing here. The important thing here is that between successive terms, you're adding a constant. So in this case, it's 1, but it doesn't need to be 1. It could be anything. It could be 10. It could be 3, as long as it's the same number that you're adding. So even if we add the sum like 1 plus 10, or let's do 0 plus 10 plus 20 plus 30, all the way to m, both of these sums, so they're both arithmetic because the difference between terms is constant. In the top one, it's 1. In the bottom one, it's 10. And so we say both these sums are theta of m squared. So you basically just take that last term, that's the important one, and you square it. And so the reason you square it is, if you think about it like geometrically, it's kind of like you're making this triangle where it's like 1 here, and then 2, 3, 4, 5, 6, and so on until you get to m. And you kind of want more or less kind of the area of the whole thing. So that's like if you like the geometric approach, you can do it like that, or there's a literal formula you can use to get that. But you don't need to know why, like how to get that. You just need to know that that is what it is. Okay, let's go into the other sum, which will pop up. It's going to be the geometric sum. Okay, and the property about the geometric sum is it's not the difference between successive terms that's constant, but it's the ratio. So we can do 1 plus 2 plus 4, 8, up to m. I think somebody forgot to mute themselves. Yeah, thanks. And if you have a question, go ahead, just interject. I think everybody can unmute themselves and ask. And for anyone new, that this is being recorded, so if you don't want your face, just don't put your camera on. Okay, yeah, so the ratio here between successive terms is constant. So for example, here, 2 over 1 is 2, and then 8 over 4 is 2, 8 over 16 is 2. So we see the ratio is always constant, or maybe an easier way is to get to the next term, you multiply by a constant instead of adding by a constant in the arithmetic sum. So in this case, it was 2, but it doesn't need to be. It could be 10, for example. It could be 1 plus 10 plus 100 plus 1,000 all the way to m. So it doesn't matter at all what the difference is, or what the difference was in the arithmetic or the ratio in the geometric. It's just the last term that matters. So again, and in this case, instead of being m squared, it's just going to be theta of m. And the reason it's m and not like something larger than m is because geometric sums just grow extremely quickly. So because they grow so fast, their last term basically dominates over all of them. Like in the case of 2, the sum of all of these terms is less than this one right here. So you'd get 15 on the left side, and then 16 is bigger than all of them, and that's true for anything. So the sum of the first m terms of this geometric sequence, or sorry, geometric series, is less than the next term, which would be 2m. So if you do that sum by hand, you'll see that that's always true. It's only for the case of 2, but the theta notation holds regardless. Oops. So as long as you know like this sum is theta of m, that's all you need to know to do the problems. Okay, and the last one is an important series. I'll just call it like log series or sequence. So it's not a sum, which is important. So like make sure like you're not summing these terms. It's like successive. So I'll put a comma in between them. So I'll say like 1, 2, 4, all the way to m. And so you're not adding these numbers. You just want to know how many terms are there here. So it's not m terms, because it would be m terms if we did 1, 2, 3, 4, 5, etc. But here we're kind of hopping by 2. And in this case, basically you can think of, I like to think of it backwards. Like if I want to go from m all the way to 1, where every term, like I go back, I need to divide by, in this case, 2. How many times do I need to divide m by 2 to get 1? And in this case, that's just the definition of log. In this case, log base 2. So that's log base 2 of m, which we only care about the theta, which is theta of log m. So it didn't need to be, just like in the geometric sum, we didn't need to be doing it by 2s. We could have been doing it by 10s or 100s or whatever, as long as it's some constant and you're multiplying between successive terms. Okay, so these are the only 3 math kind of things that you need to know. And you'll see like when we do our asymptotic analysis, we'll see these sums pop up, and then we'll just use the formulas that we didn't derive them here, that we put here. Okay, anybody have a question about any of these before we go on?
I'm a little confused on the difference between the log and the geometric, because they're just both like multiplying by 2, right? So like when do we know that like we're not summing it, but we're just like they're just different sizes?
Yeah, so we'll see that like in the examples. Basically, when you would sum it is like when you, like right now it's okay if it doesn't make a whole lot of sense, but if you have like a double for loop and your inside for loop had like these terms, so the first time it ran once, and the second time the inner for loop ran twice, and then 4 times, and so on, then you're summing them because they're all part of the same sum. And then when you get the log sequence, that would be like, maybe I can think of like a recursive problem where you do something like the function's f, right? And you call f of n over 2 inside the function. Then you're like you would basically create some tree, and the height of your tree is log n, because you have like the first level is n, is n, and then the next level is like n over 2, and then n over 4, all the way to 1, or maybe 0. Does that make sense?
Yeah, thank you.
Yeah, and we'll go over like that tree part later. Okay, so if there's no more, yeah, and to answer Diraj, yeah, this will be posted after on Piazza. So okay, so let's go into the first one. So in this case, we're given an integer n as our parameter, and here's the function, and we just want to know what's the asymptotic runtime. So this one is like, it's not too complicated because you don't have a lot going on. You just have one for loop. So we're going to start with this basic example, and then we'll work up to the more complicated ones. And I think you'll see that we can kind of use the ideas that we figure out here in the later ones to make them also pretty simple. Okay, so whenever you have a for loop like this, you should just write out the like what values I takes on. Okay, so first I will be, so let's write that. Values of I. So first I will be 0. Whoops. And then I'm going to put a comma because we're not summing anything. It's just, we're just listing the values of I. So the first value I takes on is 0. The next value it takes on, we need to look at this part here. And it says you just add 3 every time. Okay, so then it's 3, and then 6, 12, and so on. And it stops at, so it technically stops at like 2n minus either 2 or minus 1, one of those things. But we can just write 2n because we're doing asymptotics, if it's a difference of like 2 units or 3 units, that doesn't make a difference at all. So just to make the math simpler, we're just going to pretend it stops exactly at 2n. So basically, even if this if this condition was like less than or equal to 2n, it would be the same thing. So you can do tricks like that when you're doing asymptotics just to simplify some of the expressions. Okay, so we've listed all the values of I here. And no matter what the value of I is, the body of the for loop is constant work because we're just printing out I. So it doesn't matter if I is 0 or something really big like 2n, it still takes the same amount of time to print that integer out. So the body of this for loop is what we call constant. So theta 1, or you can just say constant. So we know that it doesn't matter if like I is 0 or I is 2n, the work that it does at that iteration is the same. So because we can treat all these iterations the same, we can just count how many values I takes on, and that's the runtime, because each of those contributes like 1. Each of those values of I contributes 1 to the runtime. So the total runtime is we just take the number of values I takes on. Is there any questions there? Okay, I think not. So now to actually count how many values of I, or how many values I takes on, well, one thing we can do is just factor 3 out of everything. So, and it's not a sum, so it's not like it's okay to factor 3 out because it doesn't matter if I was 2n or 2n over 3, it's the same thing, right? So here I'm just going to write all the values of I, but then just divided by 3. Oops. Okay, and so I'll write that. So these are just the values of I, but divided by 3, and we note that this is a pretty easy number of terms to count because it increases by 1 every time, and we start at 0 and we end at 2, 3 over n. So the total number of terms here is just 2/3 n, maybe plus 1 because of the 0, but we can ignore that, right? Because a difference of 1 isn't going to make any difference at all in terms of the runtime. Okay, so now we have our number of values I takes on, and now we're going to put a theta bound on that. Yeah, okay, so the reason we divided by 3 is just to make this counting easier. You don't need to, like if you can look at this sequence right here of numbers and easily count how many of those numbers there are, then that's fine. I think it's sometimes easier to boil it down to something that you're used to seeing, like 1, 2, 3, 4, etc. So that's why I like to divide by 3. But if you can count really quickly the amount of terms in the top thing, then you did not need to. Okay, so this is this number right here basically represents the number of values I takes on, and we just want to put a theta bound on that. And because we know with theta bounds, you drop any constant, we can just say that this is theta of n. Maybe I'll do this. Okay, anybody have any questions on how we did that first one?
So it doesn't matter like how much of a constant runtime, like whether it's 0, 1, 2, 3, or 2 over 3n. It just matters that there's 2 over 3n of the constants.
Yeah, exactly. So yeah, so the part where you said if it's like 1 or 2, do you mean like if there was 2 print statements here?
Or yeah.
Yeah, so then you wouldn't really, you could think of it as 2, but I would probably just think of both of those, like if there was a second print statement like right here, I would just think of both of those two print statements like counting as one unit of time. So
Oh yeah.
yeah, you basically get to define what the unit of time is, but it can't depend on the input n at all. So in this case, it's just one print statement, so that's pretty easy. But if it was two, yeah, you can just group them together and pretend like they are like one unit of time.
Okay, thank you.
Yeah. Okay. Any other questions, or we're gonna move on to the other one? Okay. Cool. So this is the PDF of this. Like if this is blurry for you for some reason, the PDF's in the Zoom chat. It has all the functions on it. Okay, so F2 is pretty similar, except now we have an inner for loop. So the outer for loop is the same exact one. It's going by 3 n to 2n. Yeah, thanks, Wesley. And the only difference is we have this new inner loop here. So we could try and like do like some, maybe you've seen in discussion doing like a sort of chart, like the one I always do is, so iteration I, and then the work at iteration I. You could try doing something like this for this problem, or you can notice something pretty simple about this inner for loop, and like quickly get the runtime of just that inner for loop. Does anyone kind of see what I'm hinting at here? Okay, well, if we were to ask like, what is the runtime of the, yeah, okay, yeah, Muhammad, do you want to expand on that answer? How do you know it's constant?
Well, we see the inner for loop is only going to run like 10 times for every iteration of the outer for loop.
Yeah, exactly. So one like quick thing to do is you don't, in this for loop, we don't see anything that's like a function of n. So we don't see n in here at all, but we also don't see I. So we only see a new variable. Well, we do see I in this print statement, but that doesn't matter because we're just printing it. So it doesn't matter how big the value I is, printing it is constant time. But like in terms of the for loop stuff, we don't see n anywhere and we don't see I anywhere. So it doesn't depend on n or I at all. So it's just constant with respect to n. So yeah, you're exactly right. This runs exactly 10 times and that's constant. So it's basically the same as what we had here, except instead of the print statement, we have like a loop that prints 10 times. So how can we use our answer to the previous one here? Is it the same or is it a little bit different?
Would it just be the same since even though there's like a factor of 10, it goes away when we simplify?
Yeah, exactly. So it would be like the 2/3 n from earlier, and then times 10 because now we're doing kind of 10 prints at every time. So that's still in the, yeah, exactly what Wesley said. It's still in the same family of functions, so it's still linear. So we can basically borrow our answer from earlier and not have to do any work at all. All right, any questions there? Yeah, I guess, Daniel, that's maybe, I don't know. Usually like it kind of just pops out at you. Sometimes it's like a gotcha sometimes. Like if you just got to notice that, oh, this inner for loop doesn't depend on I or n at all. So I can treat it as, it's like equivalent to like a print statement or some constant like function call. So I guess, yeah. But I feel like typically functions won't have like a structure like this. So usually they would look something like this, where it actually, where the inner for loop does depend on I, right here. Okay, so now we can't use the same trick as earlier. So we actually need to do kind of a different strategy. Yeah, so the strategy that I do that's pretty helpful is one, like instead of, like if it was a single for loop, that would be pretty easy, right? If it was a single for loop, we could basically use our strategy from this first question. So if you look here, it's basically a bunch of single for loops running at a in like sequentially. And so I basically mean this is the loop we're looking at, and it runs every time that this outer for loop runs. So basically we want to figure out this. So we're going to say iteration of I, and I said I because that's the variable of the outer for loop. And at some iteration of I, how many times does the inner loop run? So, or I'll just say work at iteration I. So in this case, the work at any the work at any iteration I is only done in that for loop with j. So it doesn't matter okay. The only place where I is used is in the inner for loop with j. So we can basically break it up into a bunch of different for loops running sequentially. So the first for loop is the inner for loop when I is 0. And then the second loop we're looking at is the inner for loop when I is 3, and then when I is 6, all the way to 2n. Does that make sense for what the approach is here? Okay, yeah, so basically we're leveraging our the fact that if we had a single for loop, it'd be super easy. And so we're going to break up this into a bunch of single for loops. And what should we do with all the runtime? So with all the work here, what should we do with all of them to figure out the runtime of the entire function? So we're going to get a bunch of... Sorry, go ahead.
Multiply them with an iteration?
What do you mean?
Or add them?
Yeah.
Yeah.
You should add them. So it maybe a way to think about it is, let's say this represents our total runtime. So I don't know, we don't know what it is. So let's just put Q, maybe it's some value Q. So this part of the runtime is when I is 0. This part of the runtime is when I is 1, and so on up until I equals 2n. Oops. And each one of these runtimes is basically just the inner for loop when I equals that number. I hope that makes sense. Basically, we're kind of taking a bunch of for loops sequentially, and we need to add all of them together because that's what makes up the entire runtime. Okay, so let's do that. All right, so I starts off at 0. So what I do for these is I usually like to just hop right into the the general case when you're at some iteration I, and then figure out the work as a function of I. So maybe it ends up being I don't know, 2i, or maybe it's log I, something like that. So if you can get that case, if you can figure out the work as a function of what iteration you are, then you're basically done. Then you can write out the sum pretty easily. So, but usually maybe at first you might want to go through a couple of numerical examples. So let's just start with 0 and kind of work our way up there. So at 0, so when I is equal to 0, how many times does that inner for loop run? Yeah, 0, because this condition is not satisfied. Okay, when I is 1, how many times does that inner for loop run? Yep, it's also 1. Okay, and then I think people see the pattern here. If it's 2,
Well, would we choose? Wouldn't I only be in increments of 3 since the outer loop is 3?
Oh yeah, you're right. Yeah, thank you. Yeah, 3. So actually, yeah. Okay, and then you're right. So I will be 0, 3, 6, and so on. Okay, when I is 6, how many times does it? What's the work at that iteration?
6.
Yeah, okay, 6. Okay, I think we get the pattern here. So if you're at some iteration I, then the work of that iteration is just I. So the function is like the identity. If you're at iteration I, then the inner for loop does I work. And that kind of makes sense because it looks like this, right? It's just j from 0 up until I, incrementing by 1. Okay, and then this would continue up until 2n. All right, so now we just want to add the numbers on the right. So we want to sum them. So let's write out the sum here. 0 plus 3. And so this is kind of similar to what we did earlier, except earlier we had like a comma between all of them because we wanted the sequence, but now we actually want to add them. So I hope that kind of answered your question from earlier, whoever asked that, about the commas versus the pluses. So now we can add them. I would probably factor out the 3 and do something like 1 plus 2 plus. Okay, and then now we can recognize, we see one of our sums here. So this right here is the arithmetic sum. So from here, we can conclude that the function is theta of what?
N squared.
Yeah, exactly, n squared. Okay, so yeah, so that's basically how you want to approach these iterative functions. You want to write them out as a bunch of like single for loop functions. So if you had a triple for loop, you could do something kind of similar where you have like a 3, like I guess it would be maybe a little bit trickier with 3 when you have, because then you can't do something like 2 here, but you can kind of take tricks. So one trick is like you can multiply the different, or actually maybe I have that. Is this it? All right, okay, let's go back here. So one thing is that you can kind of multiply the run times of the, like each loop, and then just multiply them together, and that's your runtime. So here, it's a little bit trickier here because this is I and not N, but let's just, for now, pretend it was N. So right now we're just gonna pretend that that says J less than N. Then you can treat each loop independently, and we know that this loop is theta of N. And then if we replace the I with the N there, we know this loop is also theta of N. And because they're nested, you can multiply them. I think that's what someone was talking about earlier when they said multiply. Then you can multiply those two things, and then you get theta of N squared as the runtime there. So pretty like quick way to do those if you have like independent loops. But then when they're dependent, like in this case, because it's not actually N, but it's J less than I, then you'd have to do like a little bit more analysis, like instead of, so it's not independent. So you would take, I guess in this case, you could take the average, like the average value here, but in general, you should probably write out the sum. So yeah, actually the average thing would only work for, I think, for arithmetic, not for geometric stuff. So if they're not independent, then just write out the sum. It probably won't be that bad. And now that you know this one, like if you ever see a loop that looks like this, you can just automatically like conclude that it's N squared runtime. So if you see this loop inside of a larger loop, like let's say I had one more loop, like int k equals 0, k less than n, k plus equals 1, like outside all of these, then the inner one, this part's independent. You know this is theta of N squared. You know this is theta of N. So you can just multiply those things and get theta of N cubed. So those are like little tricks you can take, but you can always get the right answer by working it out with a chart like this and summing. Okay. Any questions about the stuff there?
I have a quick question.
Yeah.
So is this assuming like the inside the body is like constant time? Like
Oh, yeah.
Other stuff besides like system out or printing stuff?
Yeah. So that's why over here I wrote the work at iteration I. In this particular problem, the work at iteration I was just how many times this loop ran, but it could be something else. Like it could be maybe over here, instead of printing, we do some function of j, some linear function where we pass in the parameter j, and then the work at iteration I would mean something different.
Okay.
Yeah.
Thank
So
you.
it just depends on your problem. Yeah.
I
Okay.
have a question.
Yeah, go ahead.
So in this case, you're using for loops, but in the case when you have like while loops, is it similar or?
Yeah, in the case where it's while loops, it's the same thing. You just want to know how many times does that loop run and how much work happens on each iteration of that loop. So that's why usually for asymptotics we'll do for loops, because it's just like you can just count how many times it runs because like of the parameters. With a while loop, it might like depend on some property of the input, which we'll talk about at the end when we talk about best versus worst case. So with while loops, it gets a little bit trickier because sometimes you can't pinpoint an exact number of iterations, if that makes sense.
Okay, yeah, thank you.
Yeah. All right, so we're just going to move on to F4 now. This is also an iterative one.
Wait, sorry, I just have a quick question
Yeah.
about the previous one. So did you say the runtime for F3 was n squared?
Yeah.
Okay. Doesn't the inner loop run in n squared itself, or no? It runs in n.
You mean this?
Yeah.
No, so this one runs in so this inner loop is basically the same as the first one we did, right?
Okay. Isn't that the outer loop though? The first one.
Yeah. Okay. Yeah. But so these numbers are a little bit different, but the runtime is still linear, right? In terms of this part here.
Oh, right. Okay. Yeah.
Yeah. So here in
Okay.
this one, it's linear with respect to I, not with respect to n.
Right. Okay. Makes sense.
Yeah. So that's
Okay.
why like it was 3, 3, 6, 6, and so on.
Okay. Makes sense. Thank you.
All right. So F4, we have something similar, except now we replace our inner loop with something a little bit different. It's j equals 1, j less than I, and then j times equals 2. So we're just going to do the same exact thing where we do our chart. Okay. And here, I'm just going to jump straight to like the general case. So instead of doing I equals 0, I equals 3, and so on, I'm just going to jump straight into I equals I and figuring out the work as a function of I. So, okay. Yeah, so our work here, it's basically the same as the previous versions, except because like by the same, I mean the work is how many times this inner loop with j runs, because this inside thing is constant. But here it's a little bit different because it's not really, it's something weird where you multiply successive terms with a 2. So let's figure out the work of that iteration. So at iteration I, you basically we're going to do the same thing where we write out the values of I. So the values that I takes on, where are we? The values I takes on are first 1, and then 2, and then 4, 8, all the way to I. So how many terms are there here? So that's the question we want to know, is how many terms, how many values does I take on in that inner for loop? So this is when we can use one of the expressions we derived earlier.
Wait, doesn't I increment by 3?
Yeah, but basically we've isolated to a particular value of I. So we're just pretending we're at some value of I, and now we want to know how many times, or what's the work of that inner for loop once we've
okay.
Yeah, like once we lock in a value I. Okay, I think, what is their name? Simon said log I, and yep, that's correct. So it's basically, we're just using this right here, the log sequence. So this is exactly what we have here, except instead of Instead of m, we have I. So you just substitute that in. Okay. So that's correct. It's log I. All right, and now basically you can add all of them up. So when we now take into consideration the values of I. So I is 0, 3, 6, 9, 12, all the way to 2n. And the work at that iteration is log of that number. So basically, take log of 0 plus log of 3. And basically the parameter, or I forgot what it's called, but the thing in parentheses here, those are values of I. So 0, 3, 6, and so on. All the way to log of 2n. And yeah, so one thing you'll notice is that there's log 0, which isn't really defined, but that's the reason log of 0 is there is because of, like, we wrote this out here, but in reality, if I was 0, it wouldn't run log of 0 times. It would really just run 0 times, because of the way, like, Java, or because of the way this condition is, because, like, it's j less than I, j starts off at 1, so it wouldn't do anything. So maybe we shouldn't even write that there. We can just get rid of that. Okay. Yeah, sometimes you'll see, like, weird things like that pop up, like log of 0, log of maybe you have a negative number, and just remember that you can always just kind of throw those. Like, if it's just one term, you can throw that out, because chances are, if you go back to the actual code, it probably doesn't actually run log of 0 times. It's probably just 0 because of, like, integer division or something like Java specific. Okay, we have our sum, and now we need to simplify it. So one thing I'm going to do here is use this property of logs, that the log of a times b is equal to the log of a plus the log of b. Maybe, yeah, and I'll shrink that. So basically, the hardest part about, I think, this particular problem is, like, the simplifying the sum, and it's not, like, super difficult. So, but I think that I have seen a problem like this on, I think, last semester had a problem look like this, and this is how I would do it. So after you have simplified it to a sum of logs, I'm gonna use this to kind of simplify each term, like each of these. So that's gonna be, or no, sorry, not 0, 1. So that's the first term. Now the second term. And all the way into the last term. Okay, so basically I've broken up each one of these terms here into basically taking out this is basically the equivalent of factoring out the 3. And now if we rewrite it, you'll see that it looks like this. It's going to be 2n over 3 times log of 3, because each term has log 3 in it, and there are 2n over 3 terms, plus, I guess we can put it like this, log of 1 plus log of 2 plus 3, log of 3, and so on, all the way until log of 2n, 2n over 3. Let me put a line here. Okay, so that's just simplifying it into, like, taking the log 3 out of every term. And now you can simplify this, basically reversing this part here, and you're going to multiply all of the different like arguments together. and you're going to get something that's like pretty close to n factorial, right? Because it's going to be 1 times 2 times 3 times 4 all the way to 2n over 3. So we can just write log of n factorial there, because it's close enough, right? So we're doing a little bit of asymptotics here, like before we take our theta. And then this thing over here, this is just some constant times n. So I'm going to put theta of n there. So yeah, so you have some linear term plus the log of n factorial. So in this case, you have, so yeah, so you can either leave it like this, or you can notice that log of n factorial like dominates theta of n. So basically this is a lower order term, and you can just write it as this is theta of log of n factorial. Basically just dropping that linear term because it's lower order. But if you don't know that, you could probably just leave it there and you probably wouldn't be docked. And we probably wouldn't, if we were going to do a question like this, we wouldn't do it with the +3 and the 2n. We would just do n and +1. Okay. Yeah, this is one of the trickier ones just because of the simplifying at the end. Let's box our answer. Okay, so anyone have a question on this? I'm sure there are some.
So what
why
if you?
is-
Sorry, you can go ahead.
Oh yeah. Why is log n factorial more significant than linear?
So one thing you can do, like in I think you do this in like probably 170, is that you can see that log of n factorial, or sorry, theta of log n factorial is also theta of n log n. And n log n dominates n, right? Because it has this extra like log n term here. So yeah, that's why. Does that answer your question?
Got it. So we can write it as n log n.
Yeah.
Or,
So you could write it as n log n, but like I don't think, like we had this question last semester and we accepted, or we had a question very similar to this and we accepted log of n factorial and we accepted n log n. These kinds of ones, like when it is like a sum of logs, are pretty tricky. So if we do give you a question like this, we probably wouldn't do like this 2n plus 3 business. We would just make it like, easy, like I less than n and then I plus equals 1. Because I think when you add these things, like it gets a little complicated. Okay, someone else had a question?
So could you not reduce those logs by our arithmetic sum? I guess since there's not a constant difference between them, is that
Yeah.
why you couldn't?
Yeah, that's why. So yeah, so I think are you saying like you can't, like how, like instead of doing this part here?
Like you can't somehow reduce that sum
Yeah.
other than using that log property.
Yeah, it's a little bit deceptive because it looks like it's arithmetic because you have like log 1 plus log 2, but the difference between those terms is not constant.
Okay.
Yeah. Okay. Someone said something in the chat. Yeah, exactly. What Daniel said. He's asking if, and it's not lazy. It's saving work. If you can kind of pattern match things from previous problems you've seen, and that's exactly what you should do. So if you see a problem kind of like this, first make sure it really is the same, and any differences are arbitrarily / would it make a difference in like the long term, like asymptotically, and then you can just use answers that you've seen before. So that's one. We'll see something like that a little bit down below. But yeah, so you'll see these, like if you ever see something like this ever again, log of 1 plus log of 2, and so on, then you can just use the fact that we said that it's log of n factorial. And you don't need to do that like simplification ever again.
So you also could, instead of factoring out the log 3 and having it 2n over 3, you could just leave it as a coefficient of that whole sum, right? You should have log 3 times.
Yeah, you're right.
And then that way you would see that it's a constant in front of
yeah
log n, and then you can reduce it that way.
when you get to like the later stages of like after you have your sum and you're just simplifying it, that's when you can do a number of different things to get the right answer.
Okay.
Yeah. Okay. I don't want to spend too much more time on that one because it is like kind of in anomalies because of the summing of log is just kind of weird. So we're going to move past that one. And that brings us to the recursive functions. So unless anyone had a question about any of the iterative ones, we can move on. Okay. I think I forgot to capitalize that. So sorry. All right. So with recursive problems, can I move this up? Okay, maybe not. So with recursive problems, the tactic is you want to draw out what's called a recursive tree. So I'll show you what that means. But first, let's kind of analyze what our function here is doing. So it's for recursive problems. So of course, we have some base case. So we have some base case, and then we have right here some work, and then we have the recursive call. And then this is also important, the parameter. I don't know. I don't think there's a formal name for it, but I think I usually call it like the reduction. Yeah, let's call it reduction. Oh, no, reduction in size. That's what I've said before. So, yeah, so these are the important parts of any recursive function when we're doing asymptotics. So the base case, the base case isn't super important, but it's definitely good to have in a recursive function. Otherwise, you would just recurse forever. The work we'll see here, that's going to play a very important part when we calculate the work of the entire function. And these two things down here, they determine the number of children in the recursive tree, as well as the value at each one of those child nodes. So let me show you what I mean. So somebody kicks off kind of the recursive dominoes with, they call F5 of n, right? And that will call F5 of n over 2 and F5 of n over 2. So this initial function call calls the function twice with the parameter n over 2, but it also does some work, right? And then, so each one of these functions will also do a little bit of work, and then also call off with n over 4 in this case, because we're dividing by 2. And then each one of those functions will do a little bit of work, and then kick off, and then so on. So we basically just want to add the work that each one of these nodes does at each, so we want to add the work that each one of the nodes does. And there's, depending on the type of problem, there's different techniques to try and calculate that sum. Does that, that's the high level idea of what we're doing here. Any questions about that? Okay, so usually instead of, you don't need to write F5 every time. So usually what I'll do is, let me erase this, because it's the function F5 in all cases. So usually you'll just write the problem size. So just n. And then it has 2 children. And it has 2 children because there are 2 recursive calls. And the parameter is n over 2. Okay, and then each one of these will have 2 children. And then each one of these will have 2 and so on. And now this is kind of another important part. So at some point, there's not going to be any more recursion, right? So what value is going to be the leaves of this tree? What number will I be writing here? Yeah, Dan, you're right. It's 100 because that's the base case. That's when we stop recursing. So, but it doesn't matter that it's 100. It could have been 100. It could have been 1. It could have been 0. It's as long as it's any constant, then it doesn't matter what you put. So sometimes what I'll do just to make it a little bit easier is I'll just put 1 here. because it shouldn't make a difference, right? If we do 100 extra like recursive calls, they're all constant time. So it doesn't matter if it was 1 or 100 or 0. Does that make sense to everybody? Why I can just do that? Okay. And the reason why is because it simplifies some of the like sums that we're going to be seeing here.
Wait, but if you in recursion, if you go down till say 100 versus going down till 1, doesn't that make a difference?
No, because the problem size at each one of those levels is 100 or less, right?
Oh, okay.
Yeah. So where are we? Yeah. So we've written out the tree, and now, like I said, each one of these function calls does a little bit of work, and then recurses down. So we want to find the work that each one of these nodes does, and then we'll add them all together, and that will be the work of the entire function call. So kind of the same approach as we did from our iterative one, where we wanted to find the work of something simpler, something easy, and then just add them all together. That's exactly what we're going to do here. So the techniques for this is, so sometimes the work at each level is constant. So sometimes the work at this level, the work at this level, this level, all the way to the bottom, sometimes they all have the same, like by constant, I don't mean like constant with respect to n, but I mean like they all have the same number, like they all do the same work. It's like the same expression. And if all the levels do the same amount of work, we can just take that quantity, that work, and then multiply it by the number of levels. So that's one way of doing it. Another way of doing it is if each node is constant work, so if this right here was something like just one print statement, then you could just count the number of nodes in the tree, and that would be equal to the total number of work if we summed it all together. Does that make sense why we can do those two things? Okay. And the third approach is if for some reason if the work at each level is not constant, but depends on what level it is. So this is level 0, that's level 1, 2, and so on. If the work depends on what level you're on, then you need to write like a sum out. So maybe for whatever reason, the work at level I equals like I squared, then you would need to sum over all the levels of I squared. That one in particular is a little bit difficult if it's I squared, but we don't need to do that in this case. So let's see which one we should take. So the first thing you want to check is the work at each node constant? So let's check. We just need to figure out the runtime of this for loop. So what is the runtime of this loop? If it's I starts off at n, I stops at 10n, and I gets bigger by 2 every time. And a theta bound is fine.
N squared.
Well, in the inside, we're just printing.
Oh, okay.
Yeah, so I think, yeah, Muhammad has it, right? 5n. And then when we put a theta bound, we just get theta of n. Okay, so now that we have our work, we know that the work at, like if the parameter is n, is roughly n. So now we can use that in our recursive calls. So let's write out the work here. I'll put it in like blue. So the work at this top node, we can just say is n, right? Because theta n, so we can put that there. And over here, both of these, they're both n over 2. So they both do the same amount of work. So I'll say 2 times. And now we need to figure out the work. In this case, it's n over 2. Because the work is linear and the parameter was n over 2. Okay, the next level, there's 4 things. And each one of those things does n over 4 work. All right, we didn't simplify this. This was n. And this also simplifies to n. So for the first 3 levels, it seems like the work per level is always the same. It's always n. So we can check that because let's say we're at, yeah, sometimes it glitches. So let's say we're at some level I. Well, we know that there's going to be 2 to the I nodes at that level because of the branching factors 2. And the value in that node must be n over 2 to the I because we divide by 2 every time we go down a level. So we're basically dividing by 2 I times. And that applies to n. So you can basically this is like our check to say like, yes, every every level does the same amount of work and it's n. Does that, any questions on that part? Okay, I think that made sense to most people. So now that we know every node does the same amount of work, we just need to know how many, sorry, not every node, every level does the same amount of work. Now we want to know how many levels are there. So basically, how many levels are there in this tree? Well, one thing you can do is just look at the parameter and use that to figure out how many levels there are. So the parameter, every time we go down a level, we divide by 2. So we have this sequence n at the beginning, and then n over 2, and then n over 4, all the way to 1. And that's why I made it 1, because it makes this part a little bit easier. And we want to know how many of these terms are there, because each one of these terms represents a level. So what is the expression that we should be using here?
Log n.
Yeah, exactly. So this is like from the beginning where we this is like our log sequence. So I wrote it backwards in the example you see, but it doesn't matter if you write it backwards or forwards, it's the same thing. So that means the number of levels is log n. And now we
Also,
can
isn't that the case for any bushy tree? Like log n is the number of levels.
Yeah, exactly. And that's the case for any bushy tree where you divide by 2 every time. Sorry,
Okay.
where the branching factor is well, actually it depends on both the no, sorry, it doesn't depend on the branching factor at all. It just depends on the reduction in problem size. So even
Right.
if there was only one of these calls, the height would still be log n.
Okay.
Would it be log base 2n or no? Just because it's branching.
Yeah, you're right. So it'd be log base 2. In this case, yeah, that's it's important. Well, not in this case is important, but in some cases it is important.
So why do we simplify the log n from log base 2? And
Oh, because I forgot the change of base formula, but the change of base formula shows that any 2 logs, like log base 10 of n, is equal to like some constant times log base anything you want, like 3 of n. So they're all in the same class of functions.
Okay.
Yeah. So that's why yeah, go ahead.
So because constants don't matter when we're doing the theta bound, we just simplify the log n.
Yeah, so yeah, coefficients don't matter at all. Okay, so now we know there's log base 2 of n levels in the tree, and each level does n work. So we can just multiply those two and put a theta bound. So theta of n times the number of levels, which is log n. And that's it.
I was wondering, so did we just say there's theta n work, even though it's like a I less than 10 times n, like I plus equals 2 thing, since it's going to be like about n, just estimate?
Oh yeah, so you're saying like it really should be like 5n, 5n, 5n?
Yeah, but we just simplify, okay.
Yeah, so I dropped it early on. But if we left that 5n there, then the 5 would be right here, and then because it's a theta bound, it would just go away. Yeah, so you can do tricks like that to make it a little bit easier on yourself. So you're right that it really should be 5n, but because it's theta of n, we could just replace it with n, and it would be fine. So yeah, you'll learn like if you kind of play around with these, you can modify it slightly just to make it easier to do the computation, but not actually modify the runtime at all, which is nice because it makes the math a little bit easier. All right, any questions on this tree recursion problem? Okay, and that's why you call it tree recursive, is because it makes it like this kind of tree pattern in like in terms of the function calls. So
The
yeah,
idea for the theta, like the stuff inside, is just you multiply the number or the work done at each level times the number of nodes or levels, sorry.
yeah, and that was only because each level did the same amount of work. It was all n.
Right.
Yeah. So if it was different, then you would have to write out a sum. But yeah, in this case,
Oh, okay. And then it would be that sum times the number of levels.
or no, it would just be that sum.
Oh, okay.
Yeah. Okay.
Oh, because in this case it's n for each level. Okay, makes sense.
Exactly. Yeah. So basically, you have n plus n plus n.
Log n times.
Exactly. Yep. Yep. Okay. But you might have something a little bit different where it's like 1 plus 2 plus 4 plus, I don't know. You might have something like that.
Yeah.
Yeah.
Okay.
Okay. Right. And then also another thing you can do is like what I was saying earlier with those tricks is if you look at this, you can kind of relate it to a problem that or like a function you know pretty well. And that in this case, that would be like merge sort or quick sort. And that's because asymptotically, the function does basically the same thing. So it has some amount of like linear work. So in merge sort, that's when you merge the two sorted lists. And then it has two recursive calls where the recursive, like the parameter is like getting reduced by a factor of 1/2. So in terms like of asymptotics, it basically looks the same as merge sort and quick sort. So then you can just conclude that it has the same runtime. Does that make sense, that little shortcut we can take? Okay. Yeah. So hopefully it does, because it speeds up a lot of these pretty quickly. Like if you can relate it to a problem you can just like basically skip all this work. You could just go directly from the function to the answer without drawing this. But if you need to draw this, that's fine too. It only takes like a few minutes. Okay. Here's our next recursive function. It again takes in parameter n, and we have the same for loop here. So this is the work. It's our base case. And here we only have one recursive call, and the parameter is not dividing by anything, but it's subtracting a constant. So let's see how that ends up. That's linear. All right, let's draw out the recursive tree. So the root node is going to have n in it. So that will always have n. And now there's only one child. There's not two. So we don't get a tree. We're going to get like a list, like a linked list kind of. So it only has one child, so I'll just put it directly underneath it. And it's n minus 2. And that will have a child, and that's n minus 4. And that will have a child, and it's n minus 6, and so on, all the way up until it should be 100, because that's the base case, but I'm just going to write 1, because that makes it a lot easier. Okay, so it's not really a tree. It's a little bit easier. It's just like a linear thing. And so we can just sum up the work done at each one of these levels. So because the work is it's linear, right? We just add all those things up. So this top node does a work of n before recursing. This second node does n minus 2 before recursing, n minus 4, n minus 6, all the way to 1. So our sum is, so here we're taking the same approach where you each level does the same amount of work. Or sorry, no, actually not in this case. Never mind. Yeah, I forget I said that. So this is the case where each level does a different amount of work, so we need to write a sum out. So we're just summing all the blue numbers. I'm going to write it backwards, so starting from 1, because I think you'll see it's a sum we know. So 1 came from what? Well, if I need to subtract 2 going down, then going back up, I need to add 2. So 1, or actually, you know what? That makes it a little bit trickier. So let's modify and start at 0. Yeah, so that's an example of like when it's nice to just fudge around the numbers to make it easier. So I need to add 2 if I want to go to the node on top. So that would be 2 plus 4 plus 6 plus all the way to n. So from this, I can conclude that the function is theta of what?
N squared.
Yeah, exactly. It's just our arithmetic sum, where instead of adding by 1 every time, we're adding by 2, which is totally fine.
And so then even though we know that it wouldn't actually go from 0 to 46, since those are all less than 100, we can just approximate, since n is going to be much bigger than all those, that
Yeah,
it's going to be.
you're right.
Okay.
So really, like, it's going to be this sum, but minus these terms up until 100. And that's a constant, so that's totally fine to just ignore. Yep.
Yeah. Okay, cool.
Yeah. So yeah, it makes the math much nicer. So that's one of the pluses of this analysis, is you can ignore things like that don't make a difference at all. All right. Any questions about this recursive? Yeah, and that was the last recursive function. So before we hop into like best worst case stuff, anybody have any questions about the recursion stuff? Okay, cool. The third type that we didn't, or not type, but the third strategy for the sum that we didn't do is when every node does the, when every node does constant work. So yeah, a quick example of that is like, let me see. Basically, an example of that is if you like just don't have this at all and just had 2 recursive calls. So go ahead and on your own time, if you want, you can try out a function like that and just count the number of nodes. And I think you'll see that when you count the number of nodes, that's when you're going to be using, it could be the arithmetic sum, but if in this case, I think it'll be the geometric sum, because the first layer has just 1 node, the second layer has 2 nodes, and then 4 nodes, and then 8 nodes, and so on, and you're adding all of those things. So in this case, it would be the geometric sum. So yeah. Manal, it will be posted at Piazza. Yeah. It says it's recording, so I hope it really is.
When can it be arithmetic for the if all the nodes do the same amount of work?
Oh, actually, maybe it can't be. Yeah, my bad. Yeah, it wouldn't be arithmetic. I don't think ever, because then like then it would be like 1, and then 2 nodes, and then 3 nodes. Like that wouldn't make sense. Like they would like share a child here. Yeah, my bad. I don't think it'd be arithmetic.
So it's probably always geometric.
It's probably always geometric. Yeah, my bad. Okay, you're right. Okay, other than that, any other questions on the recursive problems, or we can move on to best case, worst case? With a theta factorial. What do you mean by a theta factorial tree?
I don't know. I remember on one of the homeworks for preparing for midterm 2, they had some tree that followed something in the factorial class, and I didn't quite understand how they arrived at that.
Okay, let's see. So I guess it would have to look like something with, was it like just theta n factorial, or was it like theta of log n factorial or something?
Yeah, it might have been log. It was something within the family. If you don't remember, I think it's fine. I was wondering if there's any distinct pattern we could look for to recognize it right off the bat.
Okay, yeah, I can't think of it as of like off the top of my head, but usually I think with factorial stuff, I think you'll have like a for loop, and in that for loop you do a bunch of you do a recursive call. So you basically recurse like many different times in the function, I think. You have to look at the discussion. Yeah. Okay. So yeah, so now we're gonna be doing best case, worst case stuff. So now we can talk about the distinction between theta and O and omega. Log factorials, Joseph. Yeah, Benjamin, that's right. If you had the log of n factorial, so someone asked this. And vice versa. So theta of, and n log n is theta of, is in theta of, yeah, so these two are equivalent. Asymptotic, like when n gets really big, they're like basically the same number. Yeah, but that doesn't come up a whole lot, but it's nice to know. And you don't need to know that. It's just if you want to simplify even further for some reason. Okay, so now we talk about best case versus worst case. So this is the way I like to think about it is like you have like a number line kind of. And on here you have like, or I guess actually it would be like this. So here you might have like, or like constant time here. And then maybe here you have, I don't know, square root of n. And then here you maybe have n squared, n cubed, and you know, there's a bunch of different like tick marks you can make here. And when something is theta bounded, then you can say that no matter what, as long as n's really big, it's always going to be like right here. Like, you know, if it was theta n, it's always going to be linear runtime. It doesn't matter. No property of n can make it run faster or slower. But sometimes a function, it actually depends, like some property of the input might make it run faster. So maybe it really is like this. So maybe you can't quite pinpoint the function in all cases, but you know it's always in this range from root n to n squared. Okay, someone asked where is log n and n log n. So log n, I believe it's right here. And n log n would be like right here. So n log n is definitely right there, but I'm not 100% sure about that. So yeah, I don't think you don't really need to know which one is faster. I am pretty sure log n is faster than square root n, but I could be wrong. Yeah, so sometimes like when you can't quite pinpoint the runtime, you want to have like a range of where it would be. So if you can pinpoint it like this, so you, for example, you know the function in the best case is theta of root n, and in the worst case it's theta of n squared. Then you know it's somewhere between there, and you know that's what you can say about the function generally. So you can say it's omega of root n as well as O of n squared. So it's kind of like you can think of this as a less than or equal to, and this as a, this as a greater than or equal to, and this as a less than or equal to. So it basically bounds the runtime there. So that's kind of the idea that you can't quite pinpoint it. So instead you want to find these two bounds. And the way you find these bounds is you look at the worst case for this guy and the best case for this one. Does that make sense? Any questions about that? Okay, I think that means yes. So let's do this function and let's see where it lies. Let's actually make this a little cleaner. And I'll just remove root n because we don't need it. Okay. So here, instead of being given an integer n, we're given this array. And so the way we determine the size of the input, it depends on what the input is. If the input's just a number, then it's just the value of that number. If the input is an array here, we can treat the size as just the length of that array. So I'm choosing the parameter, like the parameter of the function, like the size of the function parameter as the length of the array, that's always what we do for arrays. Okay, so let's see what this function does. It iterates through array, and if x equals 0, it gets to return early. And if x never equals 0, then it never returns, or it will return after it iterates through all the array. So let's look at the best case. All right, can someone describe to me a length n array that would result in the best case runtime of this function?
It's n but all zeros.
Yeah, exactly. So either everything is 0 or just the first thing is 0. Both of those are totally fine. And yeah, Muhammad, you're right. In that case, the best case would be constant. So I'm just gonna say all zeros, but you could just be just the first one is 0. That it doesn't matter. It's pretty similar. And the important thing is here that the array is still length n. So sometimes you'll like, for example, in this function, maybe you say, oh, the best case runtime is constant because if n is less than 100, then you just automatically return. But you can't say that because you can't assume anything about the value of n. You can only assume properties of it. So you can't assume it's less than a number or equal to a number. You can't do that at all. But what we did here was totally fine. We just assumed that, okay, the array can be as long as it wants. It can be length n, as long as it has all zeros in it. Okay? And you're right, it would be theta of 1. So our endpoint here is here. Now let's look at the best case, or sorry, the worst case, to get the other endpoint. So can someone describe what a worst case input to this function is?
Maybe no zeros.
Yeah, exactly. Just the complete opposite. No zeros anywhere. All right. In that case, what's the runtime of the function? In the
Theta n.
Yeah, theta of n. And here we can say theta in both these cases because when you do best case, you're kind of restricting yourself to just those inputs. So it doesn't matter as long as the array has all zeros. The length of it doesn't matter at all, right? So that's what we mean by it's theta of 1. And in the worst case, the length can, whatever the length is, that's going to be the runtime of the function. So that's why it's theta in those cases, in like the best / worst case. So that means our function looks like this. It's somewhere along this line. We can't quite pinpoint it. And so that means that the function itself is omega of 1 and O of n. Does that make sense? Anybody have a question there? Okay, cool. So, all right, we can just move on to the next one. Okay, so here again, we're given, and I'm going to copy most of this because we can use it as a template. Okay. So again, we're given an array, and we're going to do the same thing where we have like n as the length of that array, and we want to know the best case and the worst case. So can someone, and yeah, so here, I didn't write out these functions, but let's just assume that they run, the first one runs linear with respect to the input, and the second one runs quadratic with respect to the input. So let's think about the best case. Can someone describe what sort of input we would want for the best case? Like what property of the array we want to assume?
The length of the array is even?
Yeah, exactly. So yeah, a length n array where n is even. Yep, and someone already said it. In that case, it would be theta of n, because I said it's some linear function. And the worst case is just the opposite.
I have a question. So
Yeah, go ahead.
we're not allowed to say like array dot length is like less than or equal to some number. What if the condition was like array dot length is less than or equal to like 100 or something? Then we're not allowed to like limit the size of n, right?
Yeah, so then we would not have a best or worst case because, or we just have there's no best case there because you can't assume n is less than 100.
Oh, okay. So it'd be like a trick question. Thank you.
Yeah, it kind of be like a trick question. Like even if we said something like, well, yeah, I mean, in general, you can only assume a property of your input, not like the size of it. So you never want to, if the questions ever has something to do with like the size of n, then you know it's like, okay, I can't factor that into my best case, worst case analysis.
There would be theta n squared for
Yeah,
the quadratic.
my bad, I forgot it. change that. Okay, so now when we draw it here on our number line, let me move this, it's kind of cluttered. So we know it has an endpoint here, an endpoint there, but we can't quite pinpoint it precisely. So we can say it's omega of n and O of n squared. Okay, and yeah, those are all the ones I have for best case, worst case analysis. The important thing is to just assume properties of your input to either make your function run as fast as possible, and if you want to do best case, or as slow as possible if you want to do worst case. But you can't assume like the parameter like n is equal to something or less than something. You still need to assume it's super, super big. Okay, any questions about worst case, best case, the omega stuff? Yeah, so yeah, that's a kind of confusing thing about, so Daniel asked, just to clarify, we use theta for best/worst cases themselves and omega and big O to describe the range. So when you do best case, you're only considering those inputs. And when you're doing worst case, you're only considering those inputs. So it's okay to theta bound those. But in the general case, you don't know anything about the inputs. You just know the inputs are really big. So in this problem, this one, it depends on if n is even or odd. So if n's really big, it could be either even or odd. You don't know. So that's why you need to use omega for the best case and then O for the worst case. Yeah. But then, yeah, exactly. So if your analysis shows that in the worst case and the best case, it's the same thing. So for however you end up getting this, you get this, then you can conclude that your function is theta bounded. So you always know it runs in linear time. Nothing about the input would make it run faster or slower. Yeah, and it's actually a double implication. So both those hold. Okay. And in here, so these are what we call tight O bounds. So we could also say that this function is O of like n factorial. That would be completely true, but it's not a tight O bound. It doesn't give as much information as this O of n squared. So when we ask for tight bounds, we don't want stuff like this. Like you can basically always say this, or like O of like n to the n, or something like super big like that. And you can always say like omega of 1. So these aren't informative. It's kind of obvious a function would be in that range. So we want as tight as possible, and to get the tight bounds, you need to look at the best and worst case, and then just throw O or omega bound on them to like get these. Okay, any questions there? Okay, yeah, we went like way over time. So does anyone have like a asymptotics question that they wanted to analyze, or if no one has a question, I guess we could just end. All right, cool. It looks like everyone's good. So yeah, I'll make a PDF of these, and then the link, the YouTube link will be somewhere on Piazza, hopefully by today. So if you're watching this to study for the final, good luck. And yeah, so yeah, that's it. So that's all I had for everybody. Hopefully that was good enough for your final, and everyone does really well on the asymptotics questions. Okay, bye
Great.
everybody.
Thanks so much.
Yeah.